Hello and welcome to all. Here we are in the canton of Wallis, more precisely in the city of Sion. You are here today at the e-learning Centre for Seismic Prevention to learn more about earthquakes. Let me introduce myself. I am Manon, and I will accompany you during this whole visit. Oops, I forgot to introduce you. This is Wallace, my super assistant. Say hello to our visitors. Wallace and I are earthquake specialists. But by the way, what is an earthquake? Why and how does the earth shake? So before testing our simulator, let's go over some key concepts. Wallace? Here is our planet, with its continents and its oceans. These continents and oceans lie on very large plates. We call them lithospheric plates. These very large, solid and rigid plates move very slowly by a few centimeters each year. In certain parts of the world, these huge plates are rubbing, colliding, and sinking under each other. The accumulated energy during these movements is suddenly liberated in the form of an earthquake. How can a very long and regular movement, like that of tectonic plates, generate something as sudden and unpredictable as the great earthquakes? To understand fully, we need to look at how our planet works. Here is our Earth. It is composed on the outside of a rigid crust, a large mantle of solid rocks, a core of liquid iron, and a solid core. How about we get a little closer? Here we can see more details. We still have our Earth's crust, which is the outer part of the lithosphere. Remember, this lithosphere is moving slowly over the asthenosphere, which is made of more deformable rocks. We also observe an oceanic ridge, where the plates diverge, and a subduction, where the plates converge. We will come back to this later. Let's take a closer look at the mantle. At its base is the core divided into two parts. The liquid core, composed of iron and nickel, has a temperature of the order of 5,000 degrees. It surrounds the solid core, which is even hotter, with a temperature of 6,000 degrees, also composed of iron and nickel, but in a solid state. The solid core grows continuously, and gradually, the liquid core becomes solid. This reaction produces a lot of heat, and this heat diffuses into the rocks of the mantle. The mantle is composed of varied rocks, most of which are radioactive. These rocks also produce heat that warms the mantle. The hot rocks are less dense. They will therefore rise towards the surface where the ridges are. They form, little by little, the oceanic lithosphere, which, like a treadmill, moves away from the ridge and moves along the surface towards the continents. During this journey, the oceanic lithosphere cools down, thickens, and becomes denser. This oceanic plate meets the continental plate in an area called the subduction zone. Having a greater density than the continental lithosphere, the oceanic lithosphere plunges under the continents, driven by its own weight. The deeper it sinks into the mantle, the more it warms up. Great movements appear in the mantle, constantly bringing hot rocks to the surface of the Earth, and the cold ones towards the interior of the Earth. These are the motor convection movements of the tectonic plates. Let's take a closer look at what happens in the subduction zone. Here the oceanic plate plunges under the continental plate. The problem is that the Earth's crust is elastic and brittle. It is not at all viscous, and therefore its movement stops at the point of contact between the two plates. In this convergence zone, the movement of the plates is extremely regular, of the order of a few centimeters per year. For this reason, we are in a permanent compression zone. This compression increases from day to day and from year to year. So then, why don't the plates slide so easily? If we take a closer look, the blocks A and B, which represent the two plates, are in contact on the rough and irregular surface of the fault. The fault is trapped by all the asperities. There is no movement. Energy continuously accumulates along the faults. Suddenly, the limit of the rock's resistance is reached. This is the earthquake. The two blocks A and B slide along the surface of the fault. But the subduction zone is not the only place where the plates move relative to one another. There are zones of compression, where the inverse faults allow the plates to converge with each other. For instance, the formation of the Alps. Look at the blocks A and B that are continuously moving closer to each other on both sides of the fault. Suddenly, the fault begins to slide, causing block B to go up and block A to go down. This is the earthquake. This same process is repeated over time, and after several earthquakes, a mountain and valleys are created. In the extension zones, normal faults allow the plates to move away from one another, like the ocean ridges. The Earth's crust stretches continuously. All of a sudden, the fault begins to slide, causing block B to go down and block A to go up. This is the earthquake. This same process is repeated over time. These thousands of earthquakes thus create land masses as well as valleys. In other parts of the world, plates A and B try to slide against each other but are stuck at the level of the fault. When the concentration of the stresses is too great, there is rupture. Block A begins to slide along the fault with respect to block B. We call this the strike-slip fault. The best-known example is the San Andreas Fault in the United States. Here you can see that the road has been shifted due to many earthquakes which have occurred over time. Now that we have understood why and how earthquakes appear, the question is how to measure the importance of an earthquake. An earthquake is characterized by its magnitude and its intensity. The magnitude measures the energy released at the hypercenter of the earthquake when the fault suddenly breaks. 70% of this energy dissipates as heat in the earth, while the other 30% is propagated as seismic waves throughout the globe. Magnitude was introduced in 1935 by Charles Richter to measure the energy released during an earthquake, so we can compare the earthquakes between them on the Richter scale. Each earthquake is characterized by a value. This magnitude is mathematically calculated from the amplitude of the movements of the soil recorded by a seismometer. Until this day, seismometers have recorded magnitudes ranging from -2 to 9.5, which corresponds to the largest earthquake registered to date in Chile in 1960. In summary, magnitude measures the energy released as a seismic wave by the earthquake. Intensity tells us the consequences of an earthquake in a given place on the Earth's surface. These consequences are determined by the European macroseismic scale that comprises 12 degrees. No instrument is needed to determine the intensity of an earthquake. It is estimated from the observations of the damage, the feelings of the population, and the geological nature of the soil. Intensity 1, the earthquake is not felt. Intensity 6, people are frightened, houses crack. intensity 10, general panic, buildings are almost all destroyed. To properly evaluate the consequences of an earthquake, a map of intensities must be constructed. So, this is what to remember. For each earthquake, there is only one magnitude. But, for each earthquake, there are several intensity values. Thank you, Wallace, for your help. There you go. Now that you know why and how the Earth starts to vibrate, you are ready to test and feel the effects of an earthquake on our simulator. See you soon!